So hello everyone, today I'd just like to clear up which of the vector space conditions here are satisfied for any subset of the vector space and which instead have to be proven. Okay, so we're just going to motivate the results of the theorem on subspaces, which is theorem 1. Okay, so let's look at the vector space conditions. Right, and the main idea is if the condition does not contain any claim that a vector must belong to V or stuff like that, then obviously it's going to hold true for a subset of V. For example, VS3, the commutativity of addition. Right? It doesn't. It says for every vector x and y belonging to V, x plus y is equal to y plus x. Right? So obviously if you're going to take a subset of V, right, this is still going to hold true, right, because the vectors belonging to a subset of V also belong to V. So VS3 is true. The same goes for VS4, right, associativity, VS5, VS6, VS7, and VS10. These are all true for a subset of the vector space. Okay? And now here comes the thing. So we have four conditions remaining. We have VS1, VS2, VS8, and VS9. And if you look at the theorem, right, the only ones we have to prove are VS1, VS2, and VS8. So how can we say that we do not have to prove VS9? Well, it's because if VS2 is true for a subset of V, then VS9 is implied. Why? Okay, so let's say we prove that there is that a certain subset of the vector space is closed under scalar multiplication, right? Then what we can do is, remember, proposition 4 says that negative x is equal to negative 1 times x. In other words, this negative x right here, right, is equal to negative 1 times x. But because we said that the subspace is the subset is closed under scalar multiplication right here, this belongs to the subset, which is let's say it's W in this case. Okay, because if x belongs to W, then because of closure under scalar multiplication, the negative 1 times x also belongs to W. Okay, so the first part is implied by VS2. Let's see if the second part is also implied. Well, of course it's implied, right? Because if this is true for the vector space V, right, then even if we take vectors belonging to the subset of V, well, they still belong to V, right? So this is still going to hold true. The second part, x plus negative x equal to 0, is going to be true for any vector in V, therefore any vector in any subset of V. Okay, so if we have scalar multiplication, then this first part is implied, right? And the second part is true just because W is a subset of V. So you might be thinking, well, okay, so if VS2 does imply VS9, then why do we even have VS9 as a condition for a vector space? And that's because it's not true that VS2 implies VS9. VS2 only implies this first part right here. It does not imply the second part, and that is the crucial point. For example, let's say that V, right, is just R2, okay, the set of all ordered couples. And I define the operation of addition as, just your standard component-wise addition. So this becomes x0 plus x1, and this becomes y0 plus y1. Fair enough. But now I define scalar multiplication as this. I take alpha times x1 comma y1, and this is equal to alpha x1 0. Okay, this is how I define scalar multiplication. Okay, so this is not a vector space, you can prove it, exactly because VS9 is not true. But let's see why it's not true. Is VS2 true? Yes, it is. Why? Because alpha, for any arbitrary alpha, alpha times x1 comma y1 is equal to alpha x1 comma 0. Is this an ordered couple? Yes, it is. Okay, so it does belong to V. Okay, so VS2 is true. So if VS2 is true, then according to our wrong logic, VS9 must also be true. Let's see. So the first part is true, okay? Because there is closure under scalar multiplication. So if we use alpha equals to -1, then clearly negative x, or better, negative x1, y1 also belongs to V. But let's see if the second part is true. So if I take negative x1 comma y1, this is equal to negative x1 comma 0. Okay, so if I calculate x1 y1 plus negative x1 0, right, I just add component wise and I get 0 y1, which is not the 0 vector of V, right? The 0 vector of V is the origin, 0 0. Okay, so the second part is not implied. Okay, this second part right here, therefore, is not implied by VS2, because in this case, VS2 is true, whereas VS9 is not true. That's because we're dealing with a vector space. If we had taken a subset, right, then a subset of a vector space, right, then VS2 being true would automatically imply VS9, exactly because it is a subset of a vector space. So yeah, that's why we do not have to prove VS9 for vector subspaces, but we do have to prove it for vector spaces.